Yes, hello, good morning. I'm going to do a video now on two topics that are very important in a lot of courses that we do. Um, Science 3102 among them, and the later physics courses and some of the math courses. And it's called, we're going to do significant digits, we're going to do scientific notation. They're very similar, very related. Okay, well, to start off, we're going to talk about significant digits or significant figures. They mean the same thing. And in my notes, I'll call these SD to save myself a little bit of time. And significant digits represent the precision of a measuring tool. So what that means, there's several consequences to that. One is that only measured quantities actually involve significant digits at all. Okay, so in a lot of your physics courses, you'll sometimes have to deduce from the question if a certain quantity involves significant digits or not. In Science 3102, it normally tells you, I believe, in a lot of the activities if you are to follow significant digits or not, but it's totally fair game for them to give you just some information and you'll have to discern if you have to use significant digits or not. So, for example, say there were 12 people in the room and they found the average height to be 5 foot 9 1/4, say, right? Or 5 foot 9 1/2. I'll say just to keep it a little bit simpler. The number of people in the room. How many did I say? Did I say 6 people? Whatever. I'll say I said six. I can't forgot it that quickly. The number of people in the room does not need to be measured. You can just look out there and say, oh, there's 6 people here. You can count them, right? So the six does not have any significant digits because it's a counted number. But the 5 foot 9 1/2, that's measured, right? That would have to be measured with, something like this, something one of these guys, right? And because we had to use a tool to measure it, then significant digits are involved. Significant digits show the smallest gradation of our tool plus 1 digit. Now, what does that mean? Well, say again, let's take a look at this measuring tape. This is a pretty standard measuring tape. I just pulled it out of a drawer. Right? We can see, let's pay attention to the centimeters part here. We see the marks on here. These show the individual number of millimeters. So say we had a line that was this long. Okay? So we can look at that line and see that it goes to 6 I'll call it 6.8 because 6.8 is going to be to here. So that looks like 6.8. And then we can estimate a little bit, right? We know it's 6 because it's past the 6th centimeter here. We know it's 8 because it's past the 8th millimeter here. And then we can estimate our next one. I'll call it 6.85 just for argument's sake. We'll call this 6.85 centimeters. So this measurement that we found here, we were sure of this 6 because it's past the 6. We're sure of this 8, and we're estimating this 5. So we can now say that this answer has 3 significant digits. Right? If we were to be so bold as to say, I think this is 6.850, or I think this is 6.852, well, that last number, we can't have that because our tool only goes into millimeters. So we can show into millimeters, we can estimate the next one, but then past that, we've got to stop. Okay? So that's sort of a beginning for why we use significant digits, is to show the accuracy of our measurements. But now, what digits are significant and what digits aren't? All right, so this is the second topic to get into, is what digits are significant. So any non-zero digits are significant. Right? So if we're given the number, say, 324, that's going to be 3 significant digits. Right? Because these are 3 non-zero digits. We'll say any zeros after a decimal and after another SD, significant digit, are significant. Now I know this one's a bit of a mouthful at first, but I think it's actually a little easy to understand once you realize this first part. Once you realize that significant digits represent the precision of our tool, it starts to become a little clearer why zeros after a decimal and after another number would be significant. Because say we had 3.20 meters, that's going to have 3 significant digits. And why is this zero significant here? Well, it's saying we know it's 3 meters, and we know it's exactly 20 centimeters afterwards. But if we had 3.2 meters, that's going to have 2 SD. Because remember, like I said up here, the last digit is the one that we're estimating. Every other digit we're sure of. Right? So here it's saying we're sure it's 3, we're sure it's 0.2, and then we're estimating it's a 0. Here it's saying we're sure it's 3, and then we're estimating it's 0.2. Right? So the presence of the 0 actually does make a difference to how precise we know that our tool is. And that's why this one, 3 significant digits, this one, 2 significant digits. Right? And then any zeros between other SDs are significant. This one's a bit more straightforward, but I say this one here to be totally thorough. Right? So say you had 6,002. That is, of course, 4 significant digits. Because the 6 is significant, the 2 is significant, so the zeros in between are also significant. But say we had 7,100.0, that's going to be 5 SD. And why is that? Well, because this 0 is significant because of our second rule, because it's after a decimal and after another significant figure. So that makes this one significant. And the 7 and the 1 are significant because of our first rule. So that then makes these 2 significant as well. Oh, I should move it over so you can see. It's not trapped behind my head. And then any other zeros are not significant. Okay, so what do I mean by that? Well, say we had 0.0021. That's 2 SD. Because these 3 leading zeros, those ones don't enter into it at all. Right? Those are not significant. Say we had 82,000. That's 2 significant digits, not 5. Right? And again, this one is 2, because we can go back up to our rule here. Right? Say we were, I don't know, measuring the number of grains of sand in a jar or something like that. We know what this is telling us is that we know it's 80,000. We're estimating there's another 2,000 because we know this one, we're estimating this one, and then the rest of these. Now, I mean, I don't know, grains of sand in a jar is a bit of a weird one, right? Because you can't measure that directly. Perhaps that was a poor example. Uh, you would have to calculate that using significant digits that you got from other sources, which does actually, thankfully, bring me to my next topic, right? Which is the topic that is in the Science 3102 assignment that is on significant figures, and that is how do we do math with significant digits, right? Okay, so there's two basic rules that we have to do for math with significant digits. Number one, when we multiply, I'll do multiplying first because it's a bit simpler. When we multiply or divide, because of course another aside, but multiplication and division are the same operation, they're just backwards, they're just inverses of each other. When we multiply or divide, our answer have as many SDs as the input number with the fewest SDs. I should put them in capitals to be consistent. Okay, what do I mean there? Well, say we had 31,000 times 294.1, and say these were both measured quantities. What we'll do, we'll grab our calculator. 31,000 times 294.1. We're going to end up with this answer here. 9,017,100. Right? But is that our answer? No. No, it's not. This is actually not... If these were both counted quantities somehow, like if this was just a math course that wasn't paying attention to significant figures, then yes, you can say this and that will be correct. But in a physics course or in a science course where we're using significant digits, or in a math course where they're talking about this topic, this would be marked wrong. Personally, maybe I would give you half marks for this, but it's still forgetting a very important part. And if the activity was specifically on significant digits, I would have to mark this totally wrong. Right? Because you have to recognize that this has two significant digits, and this has four significant digits. And because this one has two, we know that our answer needs to have two. So we need to round this to have two significant digits. So we'll call this 9,100,000. And this now has two significant digits. Our second rule for math with significant digits is that when we add or subtract, we add or subtract, our answer has the same number of decimal places as the input number with the fewest decimal places. I should say the same number of significant decimal places. Because technically any number could have as many decimal places as we wanted if we let ourselves just carry on and keep adding zeros. So let's be very precise. It needs to have the same number of significant decimal places as the input number with the fewest significant decimal places. Well, what does that mean? Well, say we had 1,300 .37, and we were to add 921.8. Let's add an extra one over here. Say we were to add these two numbers together. If we were to do it just on our calculator, just like it was a normal arithmetic sort of question in a math course, right? This will be our answer. I didn't do that intentionally to get all twos. Honestly, I didn't think this through. Just picking random numbers out of the air. 176, like so. But this is not the answer that we will get if these are both measured quantities. Right? Because this one has 3 significant decimal places. This number has 1 significant decimal place, like so. So that means our answer can't be this. Our answer needs to be 0.2. Look at that, right? It came out to be all twos. 1 significant decimal place, like so. So those are going to be our 2 rules for how we're going to do this arithmetic with significant digits. Now, an eagle-eyed viewer, a very involved viewer at this point, might be thinking, well, can't you just rewrite a number differently to have a different number of decimal places? Isn't that what scientific notation is? How do you determine if a number is going to be a decimal place or not? Right? That's an extremely apt question. Person I made up in my head, because it brings me to my next topic, which is how we represent scientific notation and how scientific notation interacts with significant digits. So scientific notation, as we might already know, is a shorter way to write very big or very small numbers. That's how it's usually introduced. And it does do that, right? So for example, say we had the speed of light in a vacuum. Right? The speed of light in a vacuum is actually very close to a round number, right? It's about, actually, I haven't remembered all the digits of it. Oh boy. Google is not cooperating with me very much right now. Okay. I'll just pick a random number. I can't remember all the actual digits of what C is. I just remember that it's 3.00 times 10 to the 8, and that's where I was going with that. Say we had the number. Yeah, I mean, let's just do that. Like so. My goodness. Okay. So say we have this number here. It's a 3 with 8 zeros following it. Happens to be the speed of light in a vacuum. in meters per second. But we can rewrite this. We could rewrite this as 3 times 10 to the 8, because that's what comes on afterwards. There is another, but this is not how we write the constant c, though. Right? And I bring this up for a reason, not just as an aside, but this is because of the second role that scientific notation plays. Is that scientific notation allows us to accurately represent the number of significant digits in a value. So what is that? What do I mean by that? Well, if you look at this number up here, a 3 with 8 zeros following it, if we go back to our rules of scientific notation, how many significant digits does that have? Just one, right? Just this 3. If I was to put a 0.0 on the end here, how many significant digits would it have? Well, it would have all of these digits, all of the 3, these 8 zeros, and then that extra 0 I added. So that would be 10 significant figures. And we're actually, the value of c doesn't have that many significant figures. The value of c that we use in most equations has 3 significant figures. But how could we write this number to have 3 significant figures? Because right now it has 1. If I put a 0.0 on there, it has 10. How do I do that? Well, what I do is I call it 3.00 times 10 to the 8. Right, if I did 3 times 10 to the 8, this has 1 SD. That's not how many I want to have. If I do 3.00 times 10 to the 8, this now has 3 SD. It's the same number, but now we've written it to have 3 significant digits instead of 1 significant digit. So this is what we want, and this is not what we want. Because when we use the value of the speed of light in a physics equation, when we put it at 3.00 times 10 to the 8, what we're saying is this value has 3 significant digits that we're sure of. Because of this property of scientific notation, we're able to use scientific notation to make it clearer how the addition and subtraction of significant digits works. Now, rather than just explain that, let me bring up a concrete example. Let me bring up the activity in Science 3102 here. So, all right, this is the multiplication page. Let me go back to the addition and subtraction page. I'll zoom out a touch so we can see the whole thing there. So calculate the following. Give the answer in correct scientific notation and correct significant digits. So I'm going to pick number 2. Number 2 is a good example of what I was just talking about. Sorry for the good paper rattling noises here on my... That's good. That's good soundscape, right? So that's good radio. This is going to be question 2. Well, it's one of many question 2s, of course, as you know if you're doing this course, because there's a lot of different pages to this assignment. So it's 1913.0 subtract 4.6 times 10 to the 3. Okay, so our first step here, our step 1, when we're adding or subtracting, we're going to convert both numbers into scientific notation with the same power of 10. Actually, I'll just move this further up in the corner like so. Okay. So, yeah, I'm not spending a ton of time here on the scientific notation part because I want to talk more about significant digits here right now. But we'll recall that when we write something in scientific notation, we put our decimal after the first non-zero digit, right? So we would call this 1.9130. That's going to be 123 times 10 to the 3 minus now 4.6 times 10 to the 3. So now both of these are in proper scientific notation. So now we can actually go ahead and subtract. Add or subtract as normal. We can even just add or subtract the values below, right? And not even worry about the scientific notation because we know that it's still going to be the same number in the corner. What I mean is, right, we're still going to have the times 10 to the 3 on the end. So we now have a negative 2.687 times 10 to the 3. We're going to round so that our answer we're going to round so that our answer has the same number of significant decimal places as the input number with the fewest decimal places. Right? So we can look back up here. This one had 4, this one had 1. So our answer is going to have 1. So if we round this number to have 1 significant decimal place, we're going to be cutting off this 8, which means this rounds up. So we're going to have a negative 2.7 times 10 to the 3. And that is our answer. That's the final thing we're going to end up with here. Say instead, I'll do one more of these ones here because I would like to show. Yeah, I'll do number 3 here then, I guess. Now I won't write out the steps here, won't belabor it quite as much, but we'll go down through it so you can see something else that happens. Because we sort of break a rule here. Now, like I said, I didn't go over scientific notation in this video. I'll make another one for that if and when I need to. But we know that in scientific notation, our decimal always goes after the first significant digit, right? So it's going to be after the first non-zero digit because you never have a leading zero that's significant. So the decimal always goes after the first non-zero digit. But here, this has 10 to the 24. This has 10 to the 23. So how are we going to get these to have the same number in the corner? Well, we've got to move one of these decimals. And remember, if the decimal goes to the right, then the number up here goes down. If the decimal goes to the left, the number up here goes up. Right? So I could call this, instead, I could say this is 23.4 times 10 to the 23 plus 1.92 times 10 to the 23. I could call that. But generally what we're going to do is the opposite. What we're going to do is we will make them, instead of making this one number go down, we're going to make this one go up. So our convention is not to do it this way, but the convention is to make this one go in the other direction. It's not really going to matter, ultimately. Actually, you know what? Yeah, just to save you some headache. Guess what? No, I'll forget that last part. Scratch that. You can move either one, either direction. It doesn't actually matter. 23.4 times 10 to the 23. Okay. Forget that I scratched it out, but I just wrote the same thing down again. Hey, you know what? Forget it. The only important part is to make sure that we have the same exponent on both. And these move like so. Then what I'm going to go do now is go ahead and just add these as normal. Like I mentioned before, it adds just like adding any old number, right? So 23.4 plus 1.92, well, that'll be 25.32. Right? I'm just going to make sure of that for the video. Seeing I'm uploading this to the internet for everybody in the world to see. Everybody in the world, by which I mean 1 to 2 of my students. Times 10 to the 23. Okay? But the thing is, what I've just done now is I've added two numbers together. This one has one significant decimal place. This one has two significant decimal places, so I can't do that. I can't have the answer have two significant decimal places. I have to have it have one, so we'll call this 25.3 times 10 to the 23. Now, to be very, very, very specific, you should write this in proper scientific notation, which we will call 2.53 times 10 to the 24. Okay. And just to show that we can indeed move it in the other direction, and it will end up doing the exact same thing, I'll just write that out over here as well. So if instead I converted them to both have 10 to the 24 in the corner, we would have our 2.34 times 10 to the 24. And now we're going to move this one instead. We're going to call this 0.192 times 10 to the 24, like so. The reason I was going to veer off and tell you to do it this way all the time is to save this step. Not terribly important. This step is not exactly hard. So you can really do it in either order. But now we're going to go ahead and add these guys like we did back over here. We're going to find we're going to get 2.532 times 10 to the 24 if I go ahead and add that. But again, we've got the same issue, right? Here now we have two significant decimal places. Here we have three significant decimal places. So our answer should actually have two significant ones. So again, this will be 2.53 times 10 to the 24, which is the exact same answer as we got here. Okay, and just to be totally thorough, I will show you one of the multiplication ones as well. Yeah, there's also something to be said about the multiplication of scientific notation in this, for this activity. This is still going to be Science 3102 assignment 2 again. But we're going to do the multiplication ones now. So what I'm going to do, I wanted to do question 2. I've scrolled down too far for my little window. (3.5) times 10 to the 2 multiplied by 6.45 times 10 to the 10. Now you can just bring up your calculator and plug these guys straight in, and your calculator will give you a very nice, very accurate, mostly accurate answer. So if I do 3.5, now on my calculator, there is this. Oh, you can't quite see because the way the focus is. I've got it manually set so it doesn't keep changing the focus on me. But there's this small capital E. A lot of calculators will use that as a shorthand for times 10 to the power of. So this is 3.5 times 10 to the 2. I'll put brackets around it just so it looks the same as the one that we've got here. Multiplied by 6.45 times 10 to the 10. Close that bracket, hit enter. And we'll end up giving us this number. Now that's skipping past a few different things, but we know this is a totally fine thing to do. It's totally legitimate to use your calculator to give yourself a preview, sort of what the answer is going to be. But I would like to walk you through the individual steps that we will go through to get there. So step 1, multiply the base numbers. So here what I'm going to do is 3.5 times 6.45, and that's going to equal 22.575. And this is to show you how to do it if you don't necessarily have a calculator that you can punch scientific notation in that easily. A lot of calculators handle it very differently. Sometimes it'll be more confusing than others. So this is the way that will always work, no matter what your calculator is. Okay, so we're going to multiply the base numbers, and we're going to get that. Step 2. So step 2, if you're multiplying, we're going to add the exponents on the tens. If we're dividing, we're going to subtract. But here we have 10 to the 2 times 10 to the 10. Well, it's going to be 10 to the 12. And this is something that you would have seen in your refresher courses where we handle the exponents. But of course, if we're multiplying numbers with like bases, we add the exponents. This is going to be times 10 to the 12. Step 3 is going to be combine and convert to proper scientific notation. So we're going to have 22.575 times 10 to the 12. But we know that this is not proper scientific notation, because in proper scientific notation, our decimal comes after the first non-zero digit. So here we have to move our decimal one place to the left, which means this number in the corner is going to go up by 1. So this is now 2.2575 times 10 to the 13. We're almost done. Step 4. Round the same number of significant digits as the input number with the fewest significant digits. So here, this number, 2 significant digits. This number, 3 significant digits. This one, 5. Boy. So we know we have to round to 2 because 2 is the fewest that we have. So our answer is 2.2 times 10 to the 13. Okay? And again, this is a way to do it no matter what your calculator is like, no matter, some of them are a little more confusing with how they handle scientific notation than others. Now, granted, pretty well every calculator, except for maybe the most basic little one, is going to be able to handle scientific notation. But I, or your in-class instructor or whomever, can probably show you how to get scientific notation to come up. Some might handle it a little touch differently, but in either case, this method here is kind of foolproof, right? These 4 steps will always work to get your answer when you multiply with scientific notation. Okay? So hopefully it's a bit clearer now why we use significant digits, what they represent. They represent the degree of precision of our measuring tools, and then basically how we're going to handle significant digits and how they interact with scientific notation.